Right, you share my screen. Yeah, the screen is shared.
Yes.
Yep.
Okay, good. So this, let's say, other type of method I have just introduced is actually driving us by simplifying quite a lot of the theory. I have to admit that. It brings us to the situation where we cannot prove that the derivative is negative definite. We can only prove that it's non-positive definite. But we can still derive the conclusion on the stability of the origin because of the argument we have used before, right? Let's look at the result. Yeah, we take again our autonomous system x dot equals f of x, where we work in a neighborhood of the origin. Again, 0 is an equilibrium point of the system, meaning or equivalently f of 0 is 0. And we assume that we have found a Lyapunov function. I mean a continuously differentiable function, which is 0 in 0. I mean in the origin. 0 is the 0 point in Rn. Positive definite on D, such that the derivative is non-positive definite. So we cannot guarantee the strict negativity and the fact that V is strictly decreasing. Now, if the set where W of x, where the derivative is 0, only contains the trivial trajectory, this is actually our reference trajectory, as I explained previously. Yeah, I mean, we refer to the origin as an equilibrium point, as stability of the origin, but we have to keep in mind that this is our reference trivial trajectory. So if the place where W is 0 contains only the set, sorry, not the place, the set where W of x equals 0 contains only, but only the trivial trajectories, yeah, and no other non-trivial trajectories, then the origin is again asymptotically stable equilibrium point. And this result is often much easier to use than the result before, than the standard Lyapunov function theorem result. Because sometimes it's very difficult to prove that W is negative definite, so strictly lower 0, strictly lower 0. Tudor, I have one question. You explained, of course, all these things with quadratic forms. What does it mean, positive, negative? This slide, you worked on it, of course. No? Yeah, he's not hearing me. Good. So this is the result now. The question is, what would we have done without this result? What would have happened? Could we have found another function which would have gone the same way? That is the good question here. Two more remarks, and here we close, let's say, the section of Lyapunov stability theorems. When we talk about global stability, means that from whatever point in Rn we take the initial condition, the trajectory will go asymptotically to the origin, right? If you look at the pendulum and what we have proved here, we have proved that only the trajectories starting in a small neighborhood around origin, with x1 minus pi will approach the origin. Only those ones, not not from the entire plane R2. And this is for sure not the case, because we have many equilibrium points in this plane, right? It's obvious that if you have several equilibrium points, you will not have global stability. But what is sometimes very important is to determine what we call the region of attraction. Yeah. Look back to the definition of stability, of even simple stability. What is simple stability? If for every epsilon positive, there exists, delta defines a neighborhood of the origin. It defines a neighborhood. Yeah, it's a ball around the origin. Yeah, there exists a delta, of course, depending on epsilon, which ensures that whenever you take the initial condition here, the trajectory will not leave the ball of radius epsilon. Moreover, if we talk about asymptotical stability, then you have stability, but also you define the origin as an attractor. I mean, there is a neighborhood of the origin from which all trajectories go to the origin. It's an attractor. And sometimes it's important to see how big this basin or region of attraction is. Yeah. How big is it? Yeah. Look, a good estimate is the set defined by the inequality V of x lower c, yeah, which should be bounded and contained in our domain. And this is a good estimate of the region of attraction. Yeah. Why? Because if I start here, V will only decrease. We know that. We know from the theory. V of x will only decrease. Yeah. But it's a good estimate because it depends on a certain value of V of x. Yeah. And in order to prove global stability, the Lyapunov function candidate that one take should go to infinity when x goes to norm of x goes to infinity. Yeah. So this is called a radially unbounded Lyapunov function because it's precisely satisfying this condition. Let me go now back to our notes just shortly. Yeah, I will take now on a separate paper. I will take just our equation and I will redenote them. We had the following system: x dot 1 equals x2, x dot 2. I will denote it like that: minus k1 sinus x1 minus k2 x2. It's obvious. K1 is j over L, K2 is k over m. It will be a little bit easier to work in our calculations. And I told you at the end of the last hour that we will go on with another type of reasoning. Look at the Lyapunov function candidate that we have picked up in first place, the energy, right? The energy was absolutely and very clear. V of x 1 over 2 x2 square plus k1, which is g over L, 1 minus cosine xn. Everything was, of course, multiplied with a constant ml square, but this is only because, we wanted to have it as energy function. But this constant can go out from here. Yeah. a whole bunch of good Lyapunov function candidates, especially when we have, let's say, polynomial systems. This is not really the case here. Here you have a system which has another special construction. The special construction is that you have here a function which you can call h of x1. And this h of x1 has some nice properties. H of 0 is 0. H is continuously differentiable on a neighborhood of the origin. And y multiplied by h of y is strictly positive in a neighborhood of the origin. If you have such a construction, one can easily look at a certain class of Lyapunov function. I will come a little bit later on that thing. But the question remains, if I want to avoid the reasoning of Lassalle, could I imagine another Lyapunov function? And one good candidate, and this is an example we will work out together now, one good candidate, I will denote it by v hat. We'll take v hat of x. Well, we will take a quadratic term. So you see, here we had a term which actually was the integration, let's put it back in blue, which actually was the integration from 0 to x1 of h of y. This is this term. You can compute it and see that k1 can go out. I could have ended up just k1 multiplied by the integral. It's the same thing if we put k1 in or not, makes no difference. Yeah. So the idea was to enlarge this term, to get v hat of x being 1 over 2 x transpose px plus this term. So plus k1, 1 minus cosine x1. Yeah, this would be what we would call another Lyapunov function candidate. Yeah, so this is a Lyapunov function candidate. Yeah, it's our job to show how it could turn into a Lyapunov function from the theorem. Make a small break and look closer to what this quadratic form could look like. Yeah? This form is the 1 over 2. X transpose is x1, x2. And P is, as we have learned, or should have learned, a symmetric matrix. So the form of P is A1, A3, A3, A2. Now I write here again x1 and x2. And this will be, you can easily see, 1 over 2 A1 x1 squared plus A3 x1 x2 plus 1 over 2 x2 squared. Is it clear for anyone, right? I have A1 x1 plus A3 x2, A1 x3 plus A2 x2, and then I multiply with x1 and x2. And this is the expression which comes out of that. Do I have to compute it or not? You tell me. We are here to look and to answer questions. Hello. Do I have to compute it or not?
No.
No. Okay. As I wanted to say at the beginning, you have small advantages with the online. But from my perspective, the main drawback is that you cannot feel as a teacher the mood of your audience. Yeah, I mean, if we are a little bit tired, we do a little bit less. If we are keen to go through harder theory, we can do a little bit more, and so on and so forth. And this is something you cannot feel, you cannot see, you don't see the people. This is why I'm saying I need your feedback. Tell me, yeah, this is not clear, or the other thing was not clear, and so on and so forth. Okay. So this is now our Lyapunov function candidate. Of course, let's check quickly. Is v of 0, 0? Yes, obviously. If all these things are here, this term is 0 in 0, so v of 0 is 0. Is v continuously differentiable on any neighborhood of the origin? It is. Well, the other question we have to answer, or condition to fulfill, is that v of x should be strictly positive for x non-zero. Yeah, and to achieve that, it's just enough to write, or equivalent to, P symmetric matrix is a positive definite matrix. Yeah. Well, this means many things. Among others, one thing is that any symmetric matrix has only real roots, and this also means that all its roots eigenvalues. Yeah, any symmetric matrix has real eigenvalues, and this condition means that all eigenvalues are strictly positive. Yeah, so this is again equivalent with lambda min, strictly greater than 0, strictly lambda max. All eigenvalues are strictly positive. And there is also another condition. The other condition is that all principal minors of P have to be also positive. Yeah. If I take the determinants one by one, Pi strictly positive for every I from 1 to n. Yeah, these conditions that I have written are from let's say, if I put here, I could count them as lambda 1 and lambda n, and n is maximum, and 1 is minimum. Yeah. All these conditions which I have written here are written in the case of n variables in state space. You have to retain that. But in our case, we just have n equals 2, right? So here n equals 2, and P is positive if and only if A1 is positive and its determinant is positive. A1, A2 minus A3 squared is strictly positive. That's all. Let's do not forget about these things. Yeah, do not forget about these things. They are important. And yeah, what would be the goal now? What do you think? Now, it would be important to write the derivative of this Lyapunov function with respect to our system, and to try to fix what is the freedom we have. K1 and K2 are given. Yeah, we cannot do too much about K1 and K2. These are given coefficients. But what are our degrees of freedom? If I start now to calculate, there is not so much place left. But if I start now to calculate the derivative of v among the trajectories, what would you obtain? What do you think? I mean, what is our freedom? How can I force? Let's put the question this way: how to get derivative of v hat? Sorry. How to get the derivative of v hat strictly lower than 0? How? What are our degrees of freedom? What is our leverage? Who are the, I don't know, the parameters or the coefficients or whatever, which will help us or could help us to get this? What do you think? No clue?
A parameters?
Yes, this is precisely the reason for which I have put these conditions. We have the freedom to get these A parameters. Yeah? We have this freedom. It's obvious for everyone that both A1 and A2 have to be positive, because A1, A2 will be positive, the product, and A1 is positive. Right, the parameters. And this is also the idea behind finding Lyapunov functions. We have certain structures which apply to certain classes of problems. But depending on the coefficients of the system, it lies in our hand to find these coefficients. Very nice. And now let's go to this calculation. I will split now the screen. I need another sheet of paper for computing that. And I will also have to rewrite the system. So we'll have x.1 equals x2, x.2 minus k1 sine x1 minus k2 x2. And we also have to write v hat of x, which is again, I will take the explicit expression in order to follow up easier. Sorry, I have forgotten the A. 1 in this case. A3x1 x2 plus 1 over 2 A2 x2 squared. Right? So far, so good. Okay. Good. Now you have both. You see quite well here. Is this okay?
Yes.
Yeah, okay. The only issue I have, but it will come a little bit later back, is okay, with the margin here, but it for now. It has to be a little bit smaller because you don't see the expression. Just a second. Sorry. Yeah, I still did not get it in the picture, but I will rewrite it. Just a second. Plus 1 over 2 A2 x2 squared. Okay, we still have a small thing left there, but it's not important. What do we have to calculate now? And I'm going back to the main calculation of the derivative. Look here. We have to calculate the derivative of v hat along the trajectories. And this will be, in our case, if I look at this sum, it will be the partial derivative of v hat with respect to x1 multiplied by x1 plus the partial derivative of v hat with respect to x2 multiplied by x2 dot. Yeah. Notice that x.1 is f1, right? This is f1 depending on x1 and x2. And x.2, this is f2 depending on x1 and x2. This is what we have here. Yeah. And the rest, once again, is a simple calculation. I will not keep these ones. Maybe the first one, the second one I will add later, right? And now you have always to be able to do at ease this calculation. Let's go on with it. It takes a little bit effort. So I have to derive v of x with respect to x1. There is no term here. We have a quadratic term here, which is, oh, I have forgotten an important term. Why didn't you pointed that for me? I have forgotten a very important term. You should have pointed that to me. Yeah, we just said, and I put that, yeah, we just said we replace the square term 1 over 2 x2 squared. So our previous candidate had a1 0, a3 0, a2 1, but we still had the term with cosine, of course. And now let's look at terms with x1. This is with x1, this is with x1, and this is with x1. So I have to derive v hat with respect to x1. What do we get? a1 x1 plus a3 x2. Sure, yeah, this is there. Right. Plus, yeah, we have the same derivative as before. The derivative of 1 is 0, minus cosine goes into sine. So plus k1 plus k1 sine x1. Now tell me to which expression I have to multiply now. Who is x dot 1? Where do I read it? I read it in the equations. Okay, system. I read it in the equation system. Who is dot x1? Equals to what? 2?
x2.
To x2. Perfect. And now I'm writing the derivative of v hat with respect to x2. This will be now blue. Yeah? Terms in x2, I have this one and I have this one. Okay, so we will have a3 x1 plus a2 x2, who is now x dot 2, which shows up here. Well, it's this entire term. So I just have to copy this expression. Minus k1 sine x1 minus k2 x2. Yeah, we have now to perform some calculations. Okay, there is not so much place left, but we will go on. Let's hope we will get some good things out of here. So I'm starting. A1 x1 x2. I will skip the next term. So I will skip this term for now. You will see immediately why. Plus k1 plus k1 sinus x1 multiplied by x2. And now I'm done here. Yeah, you see all other terms come with minus, because in this expression there is everywhere minus. So now I have to put everywhere in place minus. Then is another term that I will skip. It will be this product. I will leave it at the end. Now I'm going on further with this. So we will have minus a3 k2 x1 x2. Now I'm going with this other one along. I plus here, but of course a minus here. A2, yeah, minus A2. Yeah, we had again A3 K2 x1 x2. Now we have A2 K1 x2 sinus x1. And we also have the last term, which will be a term in x2 squared. Yeah, you have noticed a little bit why on purpose left this these terms out, because there is a sort of grouping the terms. You will see immediately why I'm doing that. So we will have a term, this one, which I skipped. A3x2 squared comes in the following form, plus, or let me write it better like that. I will put a minus here. Why not? Minus. Minus what? K2 A2 or A2 K2. And minus the term which came from here was A3. multiplied by x2 squared. Yeah, it's clear what I have did. I had the minus here, minus a2k2 x2 squared, and I have an a3 x2 squared up there. And I put a minus before. Yeah. Why do you think I'm trying to emphasize things with negative terms? And there is also this one, which I didn't write with the red. This will be minus a3k1 x1 sinus x1. Good. We want that this quantity to be strictly lower than 0 whenever x1 different from 0 and x2 different from 0, both. Yeah. For every non-zero values of x, we want this to be strictly lower than 0. And now comes my question. Yeah, it's obvious for everyone what type of calculation we are doing. Yeah, this is precisely why I kept this and split the screen. I will go back now to the calculation slide, right? So we have every partial derivative with respect to the first variable multiplied by the derivative of the first variable. But this derivative is an expression in x1 and x2. Yeah? In this case, we had here x1 dot was x2. x2 dot was this expression, right? This is what we have to do. And the partial derivatives have been computed with respect to that one. Good. Now tell me, how could one achieve the negativity of this expression? Yeah. A little bit the beauty of looking at these things closer. What can we do here to achieve negativity? Why do you think that I have put on purpose, and let's put a little bit color now here. Why do you think I have put on purpose a minus here and a minus here? Was this of any help? I mean, can these two minus be something consistent in the sense that we can guarantee for these terms to be negative? What do you think?
I would say it also depends on the sign of A1, A2, and A3.
Yeah, everything plays around these coefficients. This is what we want to show. But let's look at the terms here, because this is now the question. And I will draw, let's imagine now that we have here R2. This is our system of coordinates, x2, x1. The origin is the equilibrium here, right? And yeah, we can be in any neighborhood of the origin. I will not write anything for now. But we need some expression in x1 and x2, which is a polynomial one, second degree or second order polynomial in x1 and x2, of course with some nonlinearity. We want this expression to be negative, for sure. Again, in a neighborhood here. Doesn't matter how big, how large, it could be a stripe, it could be anything. But just around the origin, x1 and x2 are small. Good. And now let's take term by term. We have what? We have terms in x1 and x2. Yeah. Let me put the blue here. Yeah. Any other term in x1 and x2? This one. Yeah. We have this term in x2 squared. Again, red. And we have this term in x1 sinus x1. x1 sinus x1. But then we still have another terms. We have these terms in sinus x1 x2. Yeah, this is also sinus x1 x2. Good. What is the difference between the red ones and the blue ones? We have to look at their sign. No, we want this thing to be lower than 0, yeah, we have to look to their sign. Yeah, how can I achieve something lower than 0? Sum of terms which are lower than 0, each of them. Good. So my question is, can I say something about this term minus a coefficient multiplied by x2 squared? Can I say something about this, the sign of this term, of this one? Can I say something? Is the sign defined? Some of you told me it depends on the coefficient. So when is this term negative, which has a minus in front? When? How must this coefficient be in order to have it?
Positive.
Yeah. So an obvious condition for this term to be negative is to have A2K2 minus A3 strictly positive. Excellent. Once again, K2 is given, A2, A3 are at our choice, but with the assumption on the positive definiteness of P. So we have these two inequalities. A1 strictly positive, A2 strictly positive, A1, A2 strictly greater than A3 squared. Good. Fine. We are fine. So if this happens, all this term is negative. Good. I have another red term. Yeah. All these coefficients are positive. Yeah. A3 might be not positive, but of course we can also choose A3 positive. Absolutely no problem. What is the sign of x1 sinus x1 around the origin? If we take small neighborhood of the origin, what color should I choose? I will choose that. Yeah. Now here is x1. Here is sinus x1. It's different story than that. This is sinus. And this is, as you well know, this stripe we talked about, minus pi, pi. So my question remains, can we say something about x1 sinus x1? Or
Always positive.
It's
Yeah.
positive.
It's positive in the small neighborhood around the origin. So A3 positive will ensure that this term is also negative. Fine. Good. But what about the other ones? Yeah. For instance, x1 and x2 have the coefficient. I will go a little bit up. Do you still? Yeah, you still see. Yeah. So x1 and x2 have the coefficient. I will write with blue this time. A1 minus A3K2. This is the coefficient of x1, x2. And the other one, the x2 sinus x1 thing, has the coefficient K1 minus A2 K1. Yeah, so the other one is K1 minus A2 K1, x2 sinus x1. Good. Now, what about these ones? What can we do with these ones? If these coefficients are positive, I mean, if I would guarantee that, for instance, K1 minus A2 K1 is positive, does this bring something? Is this something that we can use? Let's look better at the other one, A1 minus A3 K2. Does this bring something to us? A1 minus A3 K2 positive. Can we say something about x1 and x2 or not? If we take this coefficient positive, can we say something about the sign of all this term or not? What do you think? Can we or we cannot? I'm waiting for an answer. Can we say something? How is the sign of x1, x2 in the neighborhood of the origin, in a small neighborhood of the origin? How is the sign? If you would have to decide on the sign of x1 and x2, if both positive, what is the sign of x1 and x2? Positive.
Positive, yeah.
Yeah. And if both negative, again, both positive. But here and here, in the other quadrants, they are negative. So whatever neighborhood I take around the origin, I will not have a definite sign of the product x1 and x2. Whatever, as small as this neighborhood is, it could be infinitesimally small. I will cross one of the bad quadrants. Yeah. Bad meaning that I don't have a defined sign. So I really cannot impose anything, but anything at all on the coefficients here. Why is that? It doesn't bring anything. The same situation is with x2 and sinus x1. It's the same pattern of the sign. Sinus x1 will be around the origin positive when x1 is positive and negative when it's negative, because we have seen this here. Yeah. So our function now, the derivative v hat of x derivative, or as we have denoted that in the theorem, w of x, has this expression. And I want it to be negative. What to do with the terms which have no definite signs? With these terms, we know what to do. Yeah. It was clear. I have written this already. Down here. We need A3 positive, A2K2 minus A3 positive. Right. But what should we do with these terms to avoid the annoying they bring? What should we do with these terms? I need an idea, a very simple one, but a very effective one. Remember, A1, A3, A2 are in our control. It's our leverage in getting the right Lyapunov function here. Tell me, how can we get here? How? What to do with these coefficients? No idea at all? Okay. I will go on because we're really closing to the second break. The very simple idea, people, get rid of this. These are undefined sign terms. You cannot use them when you want something to be positive or negative. Get rid of them. How do we get rid of them? Easy. A1 must equal A3K2, and this is gone. And A2 has to be 1, and this is gone. I mean, I cannot do anything about the sign, but I can work on the coefficients. Yeah. So I can really put these two quantities to 0, and I'm done. Yeah, I'm done. Don't forget the other two conditions, which were to guarantee negativity. A3 strictly positive, and the other one, A2K2 greater than A3. These were the other two conditions. And of course, we also had the initial ones for P to be positive, A1 positive, A2 positive, A1, A2 greater than A3 squared, and of course, positive. With this condition, this function becomes what? Becomes what remains here, minus A3K1 x1 sinus x1 minus A2K2 minus a3 x2 squared. And for sure, this is strictly negative. It's not non-positive, it's negative. We are done. We have proven that picking up the set of coefficients like that, and you can always do that and find, yeah, again, K2 given, yeah, A3, A2, A1 to be chosen. We are done. We have found a Lyapunov function, which makes the derivative along the trajectories strictly negative. Yeah. Negative definite. This is negative. This function is negative definite. And that's it. Just take A1, A2, A3 to satisfy these conditions, and we're done. And we were not obliged to appeal to the LaSalle type of Lyapunov functions. We just were smart enough to take a better quadratic form along the integral term, and with this better quadratic form along with the integral term, we succeeded. Just a second to go back to this one. Yeah, we just succeeded. We just succeeded, right? This was the integral term. Yeah, but we extended the quadratic term. Instead of taking A10, A20, A21, A30, we just took completely other different. Okay, I will stop here. Let's take what, a 10 minutes break to not go too late today. I will stop the recording. We just have a few slides to pass, and these are few slides